A mesmerizing and inspiring spectacle unfolded on Monday as our home star, the Sun, released a series of massive yet surprisingly weak plasma rings across its surface. This captivating phenomenon followed a powerful solar flare that erupted with unprecedented intensity. The entire event was beautifully captured in a stunning new photo display, where these ethereal rings lingered like ghostly echoes of a past solar storm. As we embark on this thrilling journey of exploration through our video presentation, we delve deeply into the complex and mysterious world of solar storms. Our focus is drawn primarily to the post-flare rings that endure in the aftermath of these dramatic solar eruptions. Despite the extensive scientific knowledge about our Sun, the exact mechanisms behind the formation and persistence of these ghostly remnants remain an enthralling mystery. Throughout this comprehensive showcase, we harness the latest advances in visual media, captivating images, and compelling videos to not only highlight the breathtaking beauty of these phenomena but also to demonstrate the immense power wielded by our closest star. Our ultimate goal is to uncover the intricate scientific foundations behind these celestial events, and shed light on why understanding solar phenomena like solar flares and their aftermath is crucial for comprehending the Sun's behavior and the dynamic forces that influence our solar system. Prepare for an immersive journey to the heart of our solar system, where the Sun reigns in all its divine splendor. On January 29, 2024, the Sun unleashed a colossal solar flare, an event of unparalleled significance in recent solar history. This extraordinary flare stands out as the most significant solar eruption recorded in the past decade, casting a brilliant light on the Sun's remarkable capacity for sudden and extreme bursts of energy. The flare of January 29, 2024, not only captured the attention of astronomers and solar physicists worldwide, but also emphasized the Sun's role as a dynamic and unpredictable celestial entity. The flare serves as a striking reminder of the Sun's inherent volatility and its powerful impact on space weather. Its intense radiation and magnetic disturbances have far-reaching consequences, affecting everything from satellite communications to power grids on Earth. Understanding and predicting such solar phenomena is vital for safeguarding our technological infrastructure and preparing for potential disruptions caused by space weather events. Moreover, this remarkable solar flare triggered a series of fascinating phenomena, including the formation of post-flare rings, lingering structures of plasma suspended in the Sun's atmosphere. These rings, cooler and dimmer than their fiery origins, persist as enduring reminders of the Sun's turbulent activities. They present scientists with a challenge due to their resilience and intricate formations, sparking ongoing investigations into the processes that govern their existence. In general, the solar flare of January 29, 2024, not only dazzled the scientific community but also provided valuable insights into the Sun's dynamic behavior. It acts as a catalyst for advancing our understanding of solar physics and space weather forecasting. By studying these phenomena in depth, scientists aim to unravel the mysteries of the Sun's magnetic fields, plasma interactions, and the broader implications for Earth and beyond. As we continue to unlock the secrets of our celestial neighbor, we are reminded of its dual nature, both awe-inspiring and potentially hazardous. Our exploration extends beyond mere observation. It is a journey to expand our knowledge of the universe and harness the Sun's power to benefit humanity. Join us as we delve into the complexities of solar storms and post-flare rings, forging new paths in scientific discovery and technological advancement. To fully appreciate the magnitude of this event, it is essential to understand the nature of a solar flare, an abrupt release of intense radiation and magnetic energy resulting from the Sun's magnetic field becoming twisted and unstable. Classified as an X-class flare, the most powerful type, this solar eruption lasted for approximately 15 minutes. The brightness emitted by the flare was so intense that it even made the event visible to the naked eye from our vantage point on Earth, despite occurring on the far side of the Sun. However, the spectacle did not end with the solar flare. It triggered another dramatic event known as a coronal mass ejection, CME. This phenomenon involves a massive cloud of plasma and magnetic field being hurled out from the Sun at astonishing speeds, estimated to be multiple times the size of Earth. The CME traveled at a remarkable speed of about 2,000 kilometers per second. While the CME was directed away from Earth, its effects were still felt on our planet. The disturbance it caused in Earth's magnetic field led to geomagnetic storms, which could interfere with satellite operations, power grids, and communication systems. Additionally, the CME amplified the solar wind, a stream of charged particles flowing from the sun, interacting with Earth's atmosphere and creating mesmerizing auroras, or the aurora borealis, visible in various parts of the world. One of the most captivating images of this solar storm was expertly captured by Eduardo Shab Babu, an amateur astrophotographer from Argentina. Using a specialized telescope and camera, he immortalized the faint plasma rings above the sun's surface, precisely where the CME had erupted. These rings, scientifically known as post-flare rings, are the remnants of the plasma expelled into space during a CME. Despite their initial fiery nature, these post-flare rings undergo a remarkable transformation, cooling down significantly and forming intricate patterns. They serve as clear evidence of the complex interaction between the sun's forces and the vastness of space. Our exploration into the core of the solar flare and the subsequent coronal mass ejection reveals not only the mesmerizing beauty and power of our sun but also the unpredictable dynamics that govern its activities. As we delve into the science behind these celestial events, we gain valuable insights that contribute to our broader understanding of the universe. So, join us on this extraordinary journey as we unravel the mysteries of the cosmos and witness the awe-inspiring phenomena left in the wake of the sun's explosive outbursts. In the wake of a solar-powered storm, the sun, our closest star and the central figure of our solar system, continues to astound and intrigue astronomers and scientists alike with its dynamic and unpredictable behavior. On January 29, 2024, a significant solar event occurred, capturing the attention of the global scientific community. This event, marked by a colossal solar flare and the subsequent coronal mass ejection (CME), offered a rare opportunity to study the sun's powerful explosions and their effects on both Earth and beyond. Solar flares are sudden bursts of intense radiation and magnetic energy from the sun's surface, caused by the rapid release of energy stored in the sun's magnetic fields, often linked to sunspots. These flares are classified on a scale from A to X, with X-class flares being the most powerful. Such events can release energy equivalent to billions of nuclear bombs detonating simultaneously. The flare on January 29, 2024, reached X-class power, emitting radiation that was detectable from Earth, even though it originated from the far side of the sun. Following the solar flare, a coronal mass ejection (CME) occurred. A CME is a massive expulsion of plasma and magnetic fields from the sun's corona into space. This material was ejected at speeds of up to several million miles per hour and can interact with Earth's magnetosphere, potentially causing geomagnetic storms and triggering auroras at higher latitudes. While the CME from January 29, 2024, was not directly aimed at Earth, its effects were indirectly observed through enhanced solar wind and disturbances in the magnetosphere. One of the fascinating phenomena observed after the solar flare was the formation of post-flare loops. These are remnants of plasma that remain suspended in the sun's atmosphere, forming intricate patterns across its surface. Post-flare loops are cooler and darker than the surrounding solar atmosphere, making them difficult to observe without specialized equipment. They can persist for hours or even days after the initial flare, providing researchers with valuable insights into the dynamics of solar eruptions and the behavior of magnetic fields in the sun's atmosphere. Understanding the formation and persistence of these post-flare loops is crucial for advancing our knowledge of solar physics. These structures are believed to be the result of processes like magnetic reconnection and chromospheric evaporation. Magnetic reconnection occurs when the sun's magnetic field lines break and reconnect in a different configuration, releasing energy in the form of heat and radiation. This process can generate new magnetic loops that trap plasma, forming the post-flare loops observed after solar flares. Alternatively, chromospheric evaporation involves the heating of the sun's lower atmosphere, the chromosphere, by the flare's energy, causing it to expand into the sun's upper atmosphere, the corona. This surge of heated plasma fills existing magnetic loops, contributing to the formation of post-flare loops. Despite these explanations, the exact mechanisms behind the formation of post-flare loops remain an active area of research, with ongoing observations and simulations aimed at refining our understanding. The study of these loops not only deepens our understanding of solar dynamics but also has practical implications for space weather forecasting. Predicting solar flares and CMEs is essential for protecting Earth's technology, including satellite communications, power grids, and ensuring the safety of astronauts in space. In addition to their scientific value, post-flare loops serve as a testament to the Sun's immense power and influence over the solar system. The Sun, a ball of hot ionized gas held together by its own gravity, generates energy through nuclear fusion in its core. This energy is radiated into space as sunlight, which provides warmth and light to Earth, supporting life on our planet. Understanding the cycles that govern solar activity, such as solar flares and CMEs, is key to understanding the Sun's role in shaping the space environment around us. Solar physicists use a range of observational techniques and instruments to study solar activity. Ground-based observatories, space telescopes, and dedicated satellites provide continuous monitoring of solar flares, CMEs, and other solar phenomena. These observations help scientists track changes in the Sun's magnetic field, measure solar radiation levels, and study the dynamics of solar storms in real time. Advances in technology have enabled researchers to capture high-resolution images and videos of solar events with remarkable detail. These visual depictions not only showcase the raw power and beauty of the Sun but also provide valuable data for scientific investigation. By combining observations from multiple sources, scientists can create comprehensive models of solar activity and improve our understanding of the underlying physical processes. In recent years, there has been growing interest in studying the Sun's impact on space weather and its potential effects on Earth. Space weather refers to the environmental conditions in space that are heavily influenced by solar activity, which can affect spacecraft, satellites, and technological systems on Earth. Solar flares and CMEs are major drivers of space weather, capable of causing geomagnetic storms that disrupt radio communications, GPS signals, and power grids. The study of solar storms and their impacts on space weather is a multidisciplinary field, involving astronomers, physicists, engineers, and space weather forecasters. Collaborative efforts between scientists and organizations worldwide have led to significant progress in predicting and mitigating the effects of solar activity on Earth's technology and infrastructure. These efforts are crucial for safeguarding satellites, spacecraft, and vital infrastructure from potential damage caused by solar storms. In addition to their practical applications, solar storms and post-flare loops also provide unique opportunities for scientific discovery and exploration. By examining these phenomena, researchers gain insights into fundamental processes such as magnetic reconnection, plasma dynamics, and energy transfer in the Sun's atmosphere. These insights not only enhance our understanding of solar physics but also contribute to broader fields of research, including astrophysics, plasma physics, and space exploration. The study of solar phenomena is not limited to Earth-based observations. Space missions like NASA's Solar Dynamics Observatory (SDO) and the European Space Agency's Solar Orbiter provide close-up views of the Sun's surface and corona. These spacecraft capture images and data from various vantage points, allowing scientists to study solar flares, CMEs, and other solar events in unprecedented detail. For example, the Solar Orbiter mission aims to study the Sun's polar regions and explore how solar activity varies with latitude. By combining data from ground-based observatories and space missions, researchers can create comprehensive models of the Sun's magnetic field and its impact on solar phenomena. These models help scientists predict the onset and intensity of solar storms and improve space weather forecasting capabilities. The ongoing study of solar storms and post-flare loops also contributes to our understanding of stellar astronomy and the behavior of other stars in the universe. Stars like the Sun go through similar cycles of magnetic activity, solar flares,